And on to question 8, they say we've got point A and B that are 0.04 meters apart as shown below. They say the sketch is drawn and not to scale. Sphere X lies 0.01 meters from point A, and sphere X has 1,238 electrons removed from the surface. So that already tells you that sphere X must be positively charged. If we remove electrons, then it means that we've got a deficiency of electrons, and that makes sphere X positive, right? So now they say, what is the nature of the charge on sphere X? Choose positive or negative. We've already said that. We know that it's going to be a positive charge. Now they say calculate the magnitude of the charge on sphere X. All right, so now what we're going to do is use our formula. We know that the number of electrons, okay, would be the charge divided by the unit charge of an electron. Actually, let me just use E there. Right, so now we're given the number of electrons that were removed. We know the charge of an electron, and so that means that Q would be N multiplied by E, and so that would be 1,238 multiplied by 1.6 times 10 minus 19. Okay, so that's minus 19. And so what that gives us in terms of the charge of the that sphere X, so that's 1,238 multiplied by 1.6 exponent negative 19. Okay, so we get a charge of 1.98 times 10 minus 16. Okay, so and that is the charge on the electron of that sphere X. All right, so remember it is positively charged. Okay, so that would be the magnitude of that charge. So that's in coulombs. All right, so they say define the term electric field. We know that electric field at a point is the area where electrostatic force is felt per unit charge, right? And that is how we define electric field intensity. So they say draw the net electric field pattern for two identical spheres with opposite charges. Okay, so what that would look like, so if we've got two spheres with two charges that are opposite, so this is what our diagram would look like. Okay, so we know that the two charges would exert forces of attraction on each other. Okay, so that is what our diagram would look like. Okay, and please remember, we know that from the positive side, so if we know this is positive, then we know that the field lines would actually be moving away, okay, or would be moving out. And we know they're moving away from the positive but moving towards the negative. So these ones would have the lines moving in. Right, and please always keep in mind that you are going to actually show, so this is negative. Okay, so if we've got one charge that's bigger than the other, right, then the field density on it should be greater than the one that has a lesser charge. Okay, so meaning more lines should appear there, and please no lines may cross each other. Okay, and make sure that they connect to the center of the sphere. Right, now the next question, they say at what point A or B is the magnitude rather of the electric field due to the charged sphere greater? Explain the answer. Now note that A would be closer to the charge, right? So we know that electric field or the force, right? So they were asking about field. it is inversely proportional to the square of the charge. Okay, so definitely it will be at A. All right, so our answer there should be A. And you can state that the field is inversely proportional to the square of the charge. So the shorter the distance, the greater that that electric field. Right, now they say to us, calculate the electric field of sphere X at point B, right? So at this point here. And they say if sphere X is now, is replaced rather, with a charge of -2 times 10 minus 9. So sphere X has got this charge which is -2 times 10 minus 9 coulombs. Okay, and what we want to calculate there, remember they said we must calculate the electric field, right? At point X. Right, so now, at point B rather. So we're going to treat B as a positive test charge. So what we're going to do there is we're just simply going to say for 8.6, right, we know that E is equal to KQ over R squared. So the electric field intensity, that would be 9 exponent 9, multiplied by the charge, remember, we said is -2. So remember, we don't need to put the sign for the charge. Okay, that tells us the direction of the field, but we don't need to substitute it into the calculation. So divided by R squared, so the distance between X and point B would be 0.04 minus 0.01. So that will be 0.03 squared. Okay, right, so let's calculate that quickly. So we've got 9 exponent 9 multiplied by 2 exponent -9. And we're going to divide that by 0.03, but remember we square that answer, so that gives us 20,000 newtons per coulomb. Okay, so remember in this case that the direction of that field, since we've got a negative charge over here, all right, so which means that it would attract that positive test charge, so it will be to the left. Okay, right, so that's how we would get the field, the electric field at X, okay, at point B. Right, now the next question, they say a negative point charge Y with a charge of -2.8 nanocoulombs is now replaced at point B. So at point B, okay, right, I'm just going to remove some of that there. Right, so we've got a charge now of -2.8 nanocoulombs, okay, that is placed there. And they say, and a point charge Z, which has a charge of 3.2 nanocoulombs at point A. So we've got positive 3.2 nanocoulombs. Okay, right, now they say to us, draw a vector diagram to show the direction of the forces on charge X, right, because of charges Y and Z. So remember, in this case, when we look at charge X, it is negatively charged. So which means B, charge B, would exert a force of repulsion, actually. So because they are both negative, so which means that B would repel charge X. Okay, so this would be the force of B on charge X, and A would actually attract that. Okay, so this is the force because of A. So this is the force, and I set E there instead of F. So this is force between B and X. This is the force between A and X. Okay, so I'm expecting the force between A and X to be much bigger because of that distance. All right, so they said we should draw that vector diagram. So we did that, showing the two forces. So this is the force of A on X. This is the force of B on X. Okay, right, so that's how our vector diagram would look like. Okay, showing us that they are going in the same direction. Now they say to us, calculate the net electrostatic force on X because of the charges Y and Z. So let's look for the force of A and X. So we're going to say this is KQA, QX divided by the distance between them, R squared. That's 9 exponent 9. The charge on A, we said that's 3.2 nanocoulombs. Please remember, nano is times 10 minus 9 multiplied by the charge on X, which is 2 nano. All right, so that's divided by the distance between A and X. Note that the distance between them is 0.01. Okay, so that gives us squared there. All right, so let's calculate quickly. In fact, we could have made that much easier for ourselves. We already had the field. So that's 3.2 minus 9 times 2 exponent negative 9. And this is divided by 0.01. Apologies there. That's squared. So I get a force of 5.76 times 10 negative 4 newtons, right? And remember, that force would be to the left. Okay, so this would be to the left. So now I need to find out what is the force of B on X. Again, we're going to do the very same thing. So I'm just going to substitute the values there. So this would be 9 exponent 9. The charge of point B, that's 2.8. And please note that you do not need to substitute the signs. Okay, and we know that X is 2 nanocoulombs. And the distance between B and X, we said this was 0.03. Okay, another way to find that force, because you already had the charge, the field rather, is that you could have multiplied the field. You can use the equation E is equal to F over Q, right? So you want the force, you already have the field, so you could have just multiplied by the charge on sphere, the charge on X. Right, so in this case, we get another value. Okay, let's try and calculate that quickly. I'm just going to change a few values at the top. Okay, so that's 2.8. And remember the distance between B and X is 0.03. Right, so again, let's find that in scientific form. That's going to be 5.6 times 10 negative 5. Okay, and remember that's newtons. They are in the same direction, so also to the left. Okay, we did specify that they are going to, sphere X would be repelled by B and it would be attracted by A, right? So in this case, what we're going to do is to find the net electrostatic field. So we are going to simply say it's going to be the force of A on X. I said A on B here. A on X plus the force of B on X. So we can actually add the two up. All right, so I've got that value there, plus the 5.76 exponent negative 4. All right, and what do we get for a final answer? Okay, so let's get that in scientific form. Okay, so, right, so we're getting all sorts of weird values there. 1.2 times 10 negative 3, is that correct though? Okay, yeah, I can see that I did something wrong there. So that's 5.76 exponent negative 4 plus, I've added 5.6 exponent negative 5. Okay, let's get that value. Yeah, so that looks like the correct one. 6.32 exponent negative 4 newtons. And so please remember it will be, even though they said, okay, so we actually need to specify the direction. Okay, so that is going to be to the left, or you can say east, rather to the west, in that case, if you wanted to use the points of a compass, right? Right, so in this case, that is how we're going to calculate the net electrostatic force. I hope that you understood that as we go to the next question.